It's one thing to listen to doom and gloom about food and fertilizer shortages, skyrocketing prices, the cost of living, or your job being outsourced overseas or eliminated due to automation. It's quite another thing to hear practical, immediately actionable advice from experts who can help you reduce the fear, anxiety, and burden of these problems. Tune in now to the Surviving Hard Times podcast from the Finding Genius Foundation with Richard Jacobs. Before we begin, a note from our sponsor. I'm Richard Jacobs, Executive Director of the nonprofit Finding Genius Foundation and host of the Finding Genius podcast. In late 2016, I was rear-ended at 65 miles an hour by a truck on the highway, which sent me off-road into a ditch. The impact of the collision gave me a concussion and other injuries. At the hospital, a CT scan showed that I had thyroid nodules, which turned out to be cancer. It was then, when I had a biopsy of my neck, that I realized even if I was a millionaire, I wouldn't want a second or a third biopsy due to the pain and the invasiveness of it. And appointments at that time for thyroid experts were 3 to 6 months out, and I was worried about dying now, even if that was irrational. So because of this, I've decided to raise money to conduct a literature review on steroids, on the causes of anxiety and depression, a condition that affects well over 50 million people in the United States and hundreds of millions worldwide. Our goal is to create a codex, a guide that reveals all possible treatments for anxiety and depression for people that live with the condition or for loved ones that have it, as my wife and my son do. To find out more about our fundraiser, visit findinggeniusfoundation.org and click on current initiatives. And now to our guest. Hello, this is Richard Jacobs with the Surviving Hard Times podcast, sponsored by the Finding Genius Foundation.
My guest is Michael Geitner. He's a Ph.D. student, a researcher in chemical engineering at Pennsylvania State University. And we're going to talk about taking the salt out of water desalination. So thanks for coming, Mike.
Thank you for having me.
If you would tell me a bit about your background, why you chose to do a Ph.D. in water desalination.
I started my undergraduate at Penn State, chemical engineering. And in terms of research, really just was interested in learning and in getting started on whatever was available. And so I had a professor who had some projects in this area with openings for undergraduates, started working on some projects looking at mainly fouling reduction, so reducing the buildup of colloidal particles or concentration of salt at the membrane surface, and then even some biofouling work.
Oh, so in reverse osmosis, you said there'll be like fouling at the membrane surface with bacterial films, and what else would happen to mess it up?
So depending on what's in the source water, you can have colloidal fouling, which is just suspended particles that, as they're removed by the membrane, tend to build up near the surface. You also get, because you're removing salt, what's called concentration polarization, where the concentration of salt right at the membrane surface is much higher than the feed water, because all of that rejected salt tends to build up in a layer there. And so that affects the membrane performance, because when you're looking at osmotic pressure, if you have now higher salt concentration on one side of the membrane, you then have more of an energy barrier to overcome to move water through the membrane, because your concentration difference across the membrane goes up.
Any high electric fields across the membrane because you have a lot of ions on one side and less on the other?
Not significantly, because all of the ions remain on one side. So you don't have a charge separation, really, at least with reverse osmosis. Your charge is still balanced. You just have a concentration gradient between pure water and saline water.
Okay. So yeah, that's really interesting. Do they have like a windshield wiper for the membranes? I know in an RO system, the dimensions are so small that it would be incredibly difficult, but I know some systems, they'll backwash, I guess, to knock stuff off the membrane. Like what are the techniques used to clear the membrane once it gets fouled too much?
Well, the windshield wiper is kind of a good analogy, because in actual operation, the membranes are set up for tangential flow. So instead of having your membrane and pressurizing your water directly over the membrane, you pressurize water and you run it across the membrane surface. And so that tangential flow along the surface actually disrupts some of that buildup and kind of sweeps away the rejected particles, salts, everything that builds up near the membrane surface. So that is one factor. You do also have periodic cleaning. So again, depending on what the problem is, you might backwash just to kind of lift things off the surface. You can also change the water chemistry, do pH adjustments if you're having problems with like scaling, like precipitating salts. And then pre-treatment also becomes very critical. So a lot of times the solution is actually how you treat the water in stages leading up to reverse osmosis. Because like with biofouling, not only do you have microbes that will attach to the membrane surface, but I think you mentioned, right, you get biofilms. So those microbes attached to the surface, they find an environment that they like, and they start to build up near each other and secrete extracellular polymeric substances. And so you get this thick film that's actually near impossible to remove once it starts. So a lot of times for that, you're talking about pre-treating the water before it reaches the RO stage. And there's a few options there. You can use like UV or ozone treatment, or a lot of times in water treatment, you add some source of chlorine to kill the bacteria. Now there's a bit of an issue there because chlorine will actually damage your RO membranes. So typically, if you're talking about pre-treatment, it can get complicated because you might have to treat the water and then treat it again to remove whatever additive before it reaches the membrane itself.
Okay, very interesting. Yeah, the reverse osmosis system, I guess there's I don't know, is there a trade-off if you have, let's say, a cylindrical wrapping of the membrane, over and over and over? The more wrappings there are, the harder it is for materials to get, let's say, all the way through the RO, or does it go tangential to each layer? And therefore, it doesn't matter how many layers are wrapped?
So typically, the setup for commercial membranes is, like you said, is wrapping membranes, and they start from a central tube that's going to collect your clean water, and you have two membranes that are back to back. So the layer that removes the salt is facing out. You put some sort of spacer between them, and then you roll them around that central tube. And you can have multiple of those. So those are called leafs, right? So you have a leaf that's two membranes back to back. Clean water collects between the two and filters to the center and then comes out of tube. Generally, with reverse osmosis, the amount of water you can produce in one of those wrapped, they're called elements, is dependent on the surface area that you have, right? How much surface can contact the incoming water kind of is a limiting step in how much water can come through. So adding more membrane to an element doesn't necessarily create an added barrier because each layer of membrane is going to filter the water independently. It becomes probably more of an issue logistically with pumping the water through a larger and larger element. So, typically beyond a certain size, then you start looking at multiple stages. So you would have RO elements in series. So you treat the water and then you have a higher concentration of salt water that will move on to another stage, and you do it in multiple passes.
Okay. So what kind of research are you doing currently in water desalination?
So in grad school, I kind of moved on to a project that's more on the side of characterization. So we use a lot of advanced microscopy techniques, namely TEM tomography, which is using a transmission microscope to take images at multiple angles, and then using those angles to reconstruct the RO active layer, the top surface that rejects salts. We can look at it in 3D. It's kind of the same principle as a CT scan that a doctor would do. You take a bunch of images at multiple angles, and then you get 3D model of what you scanned.
For a favorable setup of the membrane so that it's most efficient in being cleaned, and the trade-off of exchanging the most or weeding out the most salt. I guess there's a lot of surface chemistry and morphology involved in the membrane itself, right?
Exactly, yeah. So the focus with the imaging is on the morphology. So if you look at the surface of a reverse osmosis membrane, it's very rough. Typically, people call it a ridge and valley structure because it really looks like you're looking at a topographical map of, a mountainous region. There's protruding features. There's these deep grooves. You have variations in the density throughout the polymer film, and all of that can affect performance. So the idea is basically to look at that structure. And initially, there were some interesting findings. The student on this project before me, who's since graduated, his name was Tyler Culp. He has a couple of papers out. The first one, basically, they found that the surface area of that rough surface is much higher than previously predicted, about 2 times higher. So the imaging gives you much more insight into the top surface. And then additionally, the internal surface, after membranes are pressurized, the polymer is compressed. And that really reduces any open space in the membrane. So you're really looking at a dense polymer film there. And since then, we've been trying to then couple experimental results from actual reverse osmosis filtrations with those imaging techniques. So that's the bulk of my work, is basically looking at membranes after operation on a small scale, and then determining from those imaging results how processes like fouling and rejection occur. Kind of one of the last things that Tyler did working with some collaborators was modeling water flux in a series of membranes that had increasing flux. And the key finding there was that the more uniform the density throughout the membrane was, the higher the flux. So basically, the less variability you have in your structure, the less water has to move laterally and the more it can pass directly through the active layer. And so that's one insight into how you could design a higher performing membrane.
See that, but in terms of tangential flow, is there a trade-off where the smoother the surface, the less likely it's able to clear existing material on the surface? Or is it good all around if you get a smoother surface?
To my knowledge, smoother surfaces aren't a problem in terms of like increased fouling, because the tangential flow, you're going to create mixing at the surface from that. And then additionally, you have typically spacers that keep those membranes apart from one another in that rolled element. So you have like a plastic mesh on the surface that actually creates additional mixing. And so the length scales on the actual surface features of the membrane are, nanometer scale. They're much smaller. So they're not going to contribute significantly to that mixing.
Well, I'm picturing a really rough membrane and fluid flowing across it left to right. And if there's a particular feature that sticks out, I can see the water, flowing over it and then making like, turbulent eddies and things like that. So I can see the mixing profile would be very different and the clearance would be very different depending on the morphology of the surface.
Yes, but you also have, so if you have a protruding feature, right, you'll get mixing, but on the backside, you'll also have kind of like a dead zone, right?
Right. Would it even be, can you run them so that the flow is almost laminar with a really smooth surface across the membranes?
That's a good question.
Chemical engineering, I many years ago, but I remember they had a pipe and they estimated the roughness of the interior of the pipe and it affected the flow rates and the turbulence and all that.
Yeah,
I wonder if you guys modeled the same stuff.
Yeah, so the laminar versus turbulent flow depends a lot on your operating conditions, right? What pressure you're feeding at and all that. And you do have a point in that, a rougher surface is more likely to create some sort of mixing, right? That's even the idea behind the feed spacers there. With membrane surface itself, I don't know of any evidence that it plays a significant role in creating mixing.
Yeah, I hope it's all virtuous. I just wondered if there is a trade-off after X hours of use. If the lifetime of an RO system is 100,000 hours of use before it has to be scrapped, let's say, what does a performance profile look like for very smooth membranes versus traditionally rougher membrane?
No, that's an interesting question. So typically, if you get into smoother membranes, you're moving from reverse osmosis to what's called nanofiltration. So the roughness results from the way that the membranes are synthesized. So the way you make the polymer film that removes the salt is through, it's called interfacial polymerization. So you have basically a water phase, an organic or an oil phase, right? So two immiscible liquids, right? And each one contains a reactant. And where they meet at the surface, you have a very rapid reaction. So that's how you get the very thin film. And so the way that those reactants diffuse at that interface is what results in the rough surface of reverse osmosis membranes. Nanofiltration membranes, which have a smooth surface, have a different chemistry. So you have a different results from that reaction at the interface because the reactants are different, right? The way they diffuse is different. So direct comparison of rough surface to smooth surfaces is difficult because you also have other variables changing, because the density and the chemistry of nanofiltration membranes is different than reverse osmosis membranes because you've changed the reaction. There are other factors that play into fouling and performance data. So it's an interesting question, really. It's at the very small scale, I could see how that mixing from just surface roughness could play a role, because we've seen that small scale variations in density and other things affect flux. And it's hopefully something that some of my future work might shed some on.
Yeah, you can't do everything, but I just thought it might be an interesting factor. Or if you put spacers preferentially, if you have like a certain distance in the beginning where there are no spacers and it's as smooth as possible, and then when should you start putting in features in deliberately, like you said, spacers and all that, to to modulate the flow and along the length of the whole interaction of the liquid with the membrane. What's the optimal use of spacers and where and what heights and et cetera?
No, it's a very interesting design question. Yeah, you always have that trade-off between, like with the spacers, creating, mixing, and preventing buildup at the surface versus, smoother surface that might be less prone to fouling. Yeah, it's an interesting prompt to think about, what might be happening at the nanoscale with mixing, especially for smaller solutes like ions, right? That would be more impacted by something on that length scale.
Okay. I didn't realize it makes sense that there's so much that goes into, designing these things properly. That's very interesting. So what are you figuring out in terms of, so smoother is better, it seems like so far, but are there particular geometries that are more favorable to this interaction of the liquid and the membrane?
Yeah, so the findings so far, right, is basically the more uniform that polymer film, the higher your flux, the higher the water throughput. But we haven't really had a chance to explore what features, so whether you have, surface roughness or even internal features, so variations in density, right, might create like hotspots for fouling deposition, right? So if you have something in your water, like a scaling salt, like something that can form calcium carbonate, or even silica, which is in a lot of groundwater feeds. When it's concentrated, it will form deposits on the membrane. So if you have something like that in your feed, right, if you have a more uniform membrane, you'll have higher flux. But do you see increased fouling because of another change in the structure, right?
Yeah, like if you have a nub or a feature behind there, in the turbulent zone, I wonder if that's where bacteria would preferentially hide and make a biofilm.
Exactly. That's the type of thing that we're trying to answer now with the characterization is, beyond just making a more uniform membrane, what else can you alter in terms of the structure or the chemistry to, maybe reduce fouling, reduce the need for some of that pre-treatment? No, it's a very interesting question because a lot of the applications of reverse osmosis membranes and desalination have been optimized, right, since they were kind of first introduced. So I think these first began being really used in like the 1970s. And so over time, there's been a lot of improvements in terms of reducing the energy usage or recovering the energy from the system, been improvements in other technologies. And so they've been able to decrease the costs and improve the performance of membranes. But now that we've kind of reached this plateau, to keep pushing the limits means kind of diving into, how we can change the polymer layer itself. And so that's why we're really interested in what other impacts the features of the surface can have. And
can you dope the surface with antibacterial components, just like they would dope silicon?
Yeah, so that's an interesting question. A lot of commercial membranes for higher fouling applications are coated. So there's different proprietary coatings that companies will apply. Some of my previous work, we tried using polydopamine, which is a naturally occurring kind of adhesive polymer that we would use to functionalize the membrane in different ways. And so there are definitely options for membrane coatings. There's been a lot looked at in academic studies, a lot of times not always transferable to larger scale implementation. But yeah, there's definitely potential to functionalize membranes in a way to reduce fouling. The other interesting thing is, so I talked about chlorine damaging RO membranes, right? So if you have bacteria in your feed water, seawater source, right, something from nature in general, typically you might add chlorine to kill the bacteria, right? And then you have to remove the chlorine to run through the reverse osmosis system. And then if you're doing distribution through pipes, you might have to re-add chlorine to keep from having biofouling in your pipes as you're distributing the water, right? So one of the interesting questions is, rather than coat the surface or functionalize or keep doing pre-treatment, can we just make the reverse osmosis membranes resistant to chlorine damage? Because if your membrane can withstand chlorine, then you pre-treat, you kill your bacteria, the same water flows through your membrane and directly into your pipes. You never have any damage or degradation or loss of performance. And so that's another, both the coating approach and the direct approach to changing the membrane chemistry are interesting opportunities for us to apply the methods that have been developed through this project, where, we can look at making certain changes or adding something to the surface and how that changes the structure of the membrane and how the performance changes, and draw conclusions about, maybe making a membrane that's more chlorine resistant, also makes it less uniform in density, right? And so we have lower flux, and then we would at least know what to try to solve there instead of just kind of trial and error. Yeah, I mean, it's going to be interesting to see where things go moving forward in reverse osmosis, I think, because like I said, we're kind of at a point where a lot of things have been optimized, right? And so we're looking at fine-tuning things, especially for specific applications. So depending on what specific founts you have, right, you might have more and more products on the market tailored to specific applications,
So what results have you guys gotten already? How much of an improvement, and what are the factors? Like, what are the KPIs that you're improving on our RO system?
Yeah, so the current project is focused on the membranes themselves. So we're not looking too much at other parts of the system yet. And like I said, the most recent publication was focused on density variation within the polymer film. So the key there was that the more uniform your polymer density is, the higher flux membrane you'll have. So the next question to probably answer is, how does that play into rejection, right? So there's always a trade-off between high flux and high sol rejection, right? And I think the next step experimentally will be seeing what features in a membrane are better for removing salts and other solutes in the feed water, because then you have a way to design and optimize between the two. And then,
what about a pulse system? If you wanted to be continuous, but you do like an extra pulse where the volume goes up the flow rate goes up 20% every, 10 seconds or something. Could you do something where it's optimally cleaning the membrane? Maybe there's some sort of a resonant pulsing speed that would keep the flow rate as high as possible and keep the membrane as clean as possible.
I think that's applied a little bit in cleaning procedures. I think more with the backwashing, so not as you're running. I know, so real world system, you're generally running at constant flux, right? Because you're trying to produce a certain amount of clean water at a steady rate. So the systems are designed so that the output is constant, which means that if your performance is going down, right, you would increase your pressure to maintain a constant flux. So
why does it need to be constant? Why not just do a steady pulsing, where the flow rate will move between, move in a small range, but not a huge one? It could be made to tolerate that, no problem.
The reason I brought that up is I think the control systems would already be in place to implement that, right? Because if you already have pumping that adjusts based on, output, you could vary that, according to your own parameters. Yeah, I'm not sure. I think it would depend on the change in pressure. I'm not sure how abruptly you can lower and raise.
Yeah, it's like pulse height, pulse width, pulse.
Yeah.
Is it a ramped pulse? Is it just a step pulse? I mean, I'm sure there's a lot of things that can be played with, in the system to try to optimize flow and keep the surface cleaner too.
Yeah, no, it's very interesting concept. Yeah, it's, and like I said,
I don't know if this goes too far, but depending on the roughness factor of the surface of the membrane, I wonder if there's probably some, certain pulse ranges that would work best with, again, the roughness factor of a certain membrane and the morphology. I'm sure there's ones that would be more amenable depending on what the surface looks like. This is a guess. I don't know. It's armchair chemical engineering speculation. I'm sorry.
Yeah, that's most of what I do. So no, it's a very interesting idea. I'm trying to recall if I've seen any studies on that. I'm sure there's probably something out there, but I don't know that it's been looked into extensively. I'm sure something that could be optimized, again, based on system and membrane.
What about putting channels in the membrane deliberately along the path of flow? What would that do? If you had, a series of channels, 2 microns apart or whatever feet you wanted.
Like parallel to the surface, not through.
Right, parallel to the surface. So I'm picturing let's say I'm driving and I'm, the surface of the road is the membrane, but there's these channels, like there's edges to the road, so I don't go out of my lane. The edges would be very tall, but I just wonder if that would be a feature, and what if they spiraled around the membrane, or what if they were just straight? I don't know what that would do either.
Yeah, so there's some difficulty in patterning an RO membrane surface, right? Because the synthesis, like I said, is this interfacial polymerization. It's a very rapid reaction, right? You're basically, casting this film onto a support. It reacts very rapidly, and you get this rough surface, right? So there's not right now a lot of control over the morphology. So then you're looking at some sort of post modification if you wanted to put a pattern or ridges into that membrane surface, which is difficult to do without damaging that polymer layer, right? So if you were trying to do some sort of mechanical patterning of the surface, you're likely to cause some sort of damage that might lead to higher salt passage, more salt going through the membrane. With reverse osmosis, the target is, I think, typically greater than 99.3%. I think that's the cutoff, the lower cutoff. It's definitely greater than 99% salt rejection. So even a slight increase in your salt passage can mean that your product is no longer good enough. And then, if you're doing mechanical surface modifications, then you get into the question of, how to apply that modification. So if you did want to go that route, right, whether you're doing some sort of impression or, you have tangential motion, right, probably causes different mechanical strains that would have a different effect. So it's an interesting question because it's kind of like the opposite of a spacer, which sits on top of the membrane, right? You would have this pattern roughness built into the membrane, but definitely some more complexity in its application. It would be, I think, tricky to do without harming the membrane in some way.
Yeah, well, I mean, you're able to smooth it. I would think the smoothing would also increase the membrane integrity too. So maybe along the lines of smoothing, if you smooth it to a certain point, and then you add this feature where you do both somehow in the processing. Maybe the trade-off would balance itself out. It'll be okay. I don't know.
I should clarify. So when you talk about smooth versus rough membranes, right? Membranes that are inherently smooth, that results from the synthesis, right? Just the chemicals that are being used, right? That's the result of that reaction. When I was talking about our earlier results, talking about variability in the density of the polyamide, that's within the film, but that film still has a rough surface. So when you look at an RO membrane, right, it's going to have surface roughness. So the series of membranes that Tyler published on, the internal density of the polymer decreased in variability for higher flux membranes, but all of those membranes still have a rough surface. So even within the field of RO membranes, as you're changing the synthesis, you're not really able to get to smoothing because the synthesis so far that results in smooth membranes or nanofiltration membranes, which have a lower salt rejection. So they're not the same performance as a reverse osmosis membrane. So we're not, at least yet, we're not able to mechanically smooth our membranes after making them. It all depends on how we make them.
It's in the making. Yeah, I got you.
Yeah. Sorry, I wasn't clear on that earlier.
That's okay. What about looking at used membranes? Have you looked at them visually and inspected them and made slides in the microscope to see what you can see?
That done in industry, and it's kind of where we're steering our research is getting toward looking at membranes after they fouled, right? So in industry, there's two approaches, right? So if you have a membrane that's failed, right, it doesn't matter if your technique is destructive. So you can do what's called a membrane autopsy, where you take the membrane out of operation and you can do all sorts of chemical staining and you can cut it apart and you can look at the damage to the membrane and determine what went wrong, right? Because you already know that membrane's not usable again. If you're trying to do it during operation, that becomes a little more complex because you're testing without damaging the membrane, right? So the techniques that we use are more in lines of an autopsy, because in order to do electron microscopy, we have to cut apart our membrane and isolate the top layer of the membrane. So we can do something similar. We're looking at much smaller length scales, right? But yeah, we can essentially take a used membrane that's been fouled by different feed waters and see the differences in how those foulings build up on the membrane surface. Right. So, if you're looking at something like silica, which, is forming small deposits in its initial stages versus, particles, which are just being kind of mechanically deposited on the surface, versus bacteria, right, which are going to have some sort of preferential area where they attach and start a biofilm. We can look at those membranes and the structure surrounding those phthalates and start to gain some insight into, okay, does phthalate always occur at a high density region? Does it always occur at a highly charged region, or does it depend on the species? So that's a big part of what we're trying to do. And based on the results, right, you get into, if you know that a certain feature is always going to promote biofouling, right? Then if you have an operation that's very prone to that has problematic feed water in that regard, then you can design and select products for that application based on the findings from those small scale studies. And I really do think, moving forward, I think things are going to become more and more tailored to specific applications. Like I said, it's in order to really optimize further and get better performances from where we are, I think. And it's already done to a large extent, but I think there's going to be more design based on niche applications.
Okay. Interesting. Last thing I thought of is, what if you get a pulse of ultra-pure water to clean, the RO system? You're keeping it flowing, but you put in, I don't know, half a liter of ultra-pure water, run it through, and maybe it strips off a bunch of the salt. And then you put in normal stuff, and it's like you rework the filter, you freshened it up. Has anyone done that?
So ultra-pure water, I believe, is lower pH. Is that correct?
Oh, well, I mean, ultra-pure should be right around 7, I would guess, because you strip out as much as you can out of the water. Like I worked in a fab for Motorola and Intel, ultra-pure water for the semiconductor manufacturer. It's actually very dangerous because there's nothing in it. It sucks up minerals and the stuff like crazy.
Yeah.
I wonder if that was put through an RO system, a quick pulse of it, and then you return to the normal flow, if that would strip off enough salts and other materials and maybe even kill the biofilm. Because it probably would. If it hit a biofilm, it probably would tear apart the bacteria and everything. So just think it.
That's an interesting approach to cleaning, because a lot of it is typically like pH changes or mechanical backwash. I mean, so essentially what you're doing is you're taking your feed water, you're replacing it with water that has nothing in it, right? So I would definitely think anything that's not attached to the membrane surface. So if you have, concentration, polarization, just salt buildup near the membrane surface, if you have particles that are kind of sitting there but aren't really attached, I think it would reduce all of that. In terms of biofouling, if you kill the microbes, you'll definitely arrest biofilm formation, right? I still don't think you'd be able to remove a biofilm once formed. I think that's, even if it's killed, it's still going to stay on the membrane surface just because of those EPS substances that bind the microbes together. I don't know enough about EPS chemistry to know if the ultra-pure water would have an impact on that, so it might. But yeah, I think switching your feed to something that's entirely clean already, right, will definitely have some sort of cleaning effect. Will definitely remove and flush out a lot of what's in there and reset things. I don't think it would be a cure-all, right? I think there's some problems that it wouldn't have an impact on. But I think that's also true of any cleaning process right now, right? Again, it depends on the problem you're dealing with. So I think all of the things you mentioned could be useful in different applications,
Okay, well, very good. Well, Michael, what's the best way for people to find out more about your work and maybe see some images if you have some papers that you read? Where can they go to look and find out more about your lab and its work?
Sure. So right now I'm working with Enrique D. Gomez at Penn State University. So he has a research website with recent publications, and you can follow his citations and find the papers related to this. And then my former advisor, if you're looking for membranes research in general, his name is Manish Kumar. He's actually at UT Austin right now, and so those would be some good starting points to get our work specifically and some related work.
Okay, excellent. Well, very good, Mike. Thank you so much for coming on the podcast. I really appreciate your time.
Thanks so much for having me. It was a very interesting discussion, and appreciate the invitation.
Before you stop listening, ask yourself, what are 1 or 2 useful things you heard on this podcast that can help you overcome food and fertilizer shortages, skyrocketing prices, the cost of living, or your job being outsourced overseas or eliminated due to automation? Please like and subscribe and tell your friends and family about their Surviving Hard Times podcast. We're all going to need help now and in the near future.